Okay, now I will start the gradient. So first of all, let me write the formula. A gradient of a scalar function t can be represented by this. I mean, it can be represented by this del by del of t. Okay, so what is this del? We will see it later, but let me write the formula first. Okay, so it is del by del x t with x cap plus del by del t y cap plus del t by del z cap. Okay, so of course this gradient operator, so will take a scalar. Okay, so what it does, it take a scalar or maybe a scalar field, you can say. Okay, here we are taking this t and it will produce a vector or a vector field, which is the del t. And the I mean, this is just a symbol. This del is a symbol. It is called the del operator. Okay, so if we expand this, so it would look like this. But remember, this is only valid. This formula is only valid for the Cartesian coordinate system. If we are writing expanding the vector in the I mean, if we are just expanding this del operator in the other coordinate system like spherical, polar, or the cylindrical coordinate system, the exact equation would look like totally different. And we are going to see in the upcoming videos about the different coordinate system as well, and how we can just derive the expression for the gradient in those coordinate system. Okay, so now okay, so now let's come to the now let's come to something that we have to see. So suppose we have a function. We are taking the one dimensional function, I mean one variable function, I'm sorry. So this is the y, this is the x, f of x. Okay, so how we will look at the change of f? Okay, so we are just looking for the change of f. Okay, so what is it? It is the limit del of f. Here limit if it is a function of x, the x tends to 0. Okay, what is this change? Well, this change can be represented by this df by dx. You may say that this del dx and this dx will cancel out and it will give df, but this is wrong. Okay, this interpretation is actually wrong. What I should say instead, that this particular quantity itself represents some physical thing. Okay, so let me give you an example. Okay, so suppose you go to the market and you buy you buy two maybe 10 pencils. Okay, and the price, or we can say rate of the pencil, the rate is actually the price of one unit material. Okay, so the rate of one pencil is actually, let's say, 5. So how many total cost of the pencil will be? So that is nothing but the rate into total pencil. Rate into total number of pencils. Okay, so here rate is 5 and total pencil is 10, total 50. Okay, so what we are doing, if we find what is the total values. So what we do, we multiply rate with the total amount of thing that we are taking. Here we are taking the pencil from the market. In similar way, the change in this function f can be given by the rate at which this function change with respect to x times how much x is changing. So this idea actually comes from this basic mathematics that we learned in our in our school. Okay, so we have to understand this says df by dx is actually the rate at which the function f is changing with respect to x times how much x has changed, and multiplication of these two will actually give how the whole function is changing. So why are not okay, one thing, why are not we writing this as a df partial derivative of f with respect to x? Because here we have only one variable function, right? We have only one variable function. So either we write this, either we write like ordinary derivative or partial derivative. The meaning is always same in this case. Okay, so suppose we have a two-dimensional function. So what we can write? So now this f is a function of x as well as y. So now this df by change in function x is, how can we write? Okay, so how the f is changing? F can be changed by changing x and y. So first of all we will write how f is changing when x is changing. Okay, and then after that we will add with that how f is changing if y is changing. So the f changes because of two reasons. One is due to the x and the other is due to the y. So we will first write the expression for first variable and the expression for the second variable after that. So df is partial derivative of f with respect to x, the rate of change of f with respect to x times how x is how much x has changed, plus, because the total change always summed up of the individual changes. Okay, the partial derivative of f with respect to y, how f is changing when y is changing, times how much y has changed. Okay, so this is the total change of function f of two variable. If we want to write for the three variable, we will add here one another term. Okay, del f by del z dz. Okay, so we know this. Now why we are doing this? We are doing this because we want to come to this point. Okay, so let's do this. So for the three variable, let me rewrite this equation. Partial derivative of f with respect to y dy is partial derivative of f with respect to z dz. Okay, so what we can do now, we can write like this. Okay, x cap plus y cap plus z cap. Now dot product with x cap dx plus y cap dy plus z cap dz, and I'm pretty sure you all are familiar with this two expression individually, what this two expression is representing. First of all, we have already learned this is the infinitesimal displacement vector, okay, which can be represented by either dr or maybe represented by dl. And what is this expression? This expression is actually the above expression that we have wrote down. Okay, instead of t we have choose f. Okay, so this can be written as del of f dot dl.